still have another minute or so.
Yep. So we're going to kick off in about 3 or 4 minutes. What we're going to do is we're going to do like 30 minutes of just talking about rapids in general. I'm going to talk for the first half, and then I'm going to de-mic and then pass it to Keith. And then after that, we have about 50 instances of GCP. So hopefully everything will work where everyone can just grab an instance. It should be pre-installed with cuDF and QML. Play around with it. There's some data sets already loaded in the NFS that's attached to the instance.
No data sets.
No data sets. Okay, so grab your own data sets. But they can be downloaded from the...
yeah, you can download whatever data set. You can generate random data. But
and we also have the... we can just grab like the first year of data from the mortgage.
Sure.
Yeah. And then also, if anyone... we have kind of... Oh, we're not starting yet. Yeah, we're just kind of just... Yeah. And anyway... and so afterwards... either play around with rapids, or if people want to, a lot of the developers are here. So if there's any issues in rapids that you're like, hey, you know what, this issue is a really small issue, I just want to fix it, we would love for people to do that as well. And so, just like hack at rapids and add some functionality. We're just going to try to experiment with that today. So y'all are kind of like our guinea pigs for this like rapids hacking of functionality.
I like the reference.
I'm glad I got one person.
I think we lost video.
Did we lose video?
Yeah.
Wait.
Try just unplugging the mini display port and plugging it back in.
That's annoying.
We lost video on the TVs.
Yeah, so my computer still thinks it's...
Yeah, the computer is sending a signal.
It's probably technology. Pull off the connection.
Yeah, so that, like right now my screen is showing that I'm sending something. It's sending a signal, it's just not. Yeah. And I switched.
You switch it?
Yeah.
Definitely.
Do we have any more slack on the HDMI?
No. You can just watch it like right on that box. Make sure the connection.
Actually, you know what we can do? Let me try this.
Don't unplug the box.
No, I'm not. Going back to my old school AV days.
You guys, Josh and Keith?
Yep.
Hey guys.
Hey, how's it going? Nice to meet you.
Nice to meet you.
Yeah. Nice to meet you.
So we lost our screens, huh?
Yeah, so it's
The
sending a
computer
signal.
thinks it's sending a signal. It's just not getting to the TVs.
Yeah.
Oh man, okay, so maybe you guys set up the splitter, which I guess is this thing.
Yep,
Yeah.
and it was working like 2 minutes ago,
Okay.
Yeah.
and then it just stopped.
Is it possible that it got sort of, the power got kicked and, is it on?
I think it's on. My computer's still charging.
Huh. Alright, well, let me go fetch the VG thing. Because this seems like an essential part of doing,
Solid start.
Yeah, push come to shove, we could always just take the splitter off and just use one monitor. One half of the room will be happy. The other half will just disappear.
I think this is where you do stand up and stop.
Well, that was what my Thanos joke was for. Half the room would be happy, the other half would disappear. God.
So when you're ready to switch, you can just do the switch hand empty stuff, put them in the pocket and tip it. Real quick, right?
Yeah, we'll just unplug it and just, just hand
You
it.
tip it.
Yeah, that's fine.
Yeah. He's not even wearing a jacket, so it's easy.
Yeah.
That's fine. you guys here.
Awesome.
Coming out of here?
Yeah, over here.
Out of here.
Yep. There.
You turned it off and on already?
Don't think so.
Pops up. You got anything else?
Oh, there we go.
You need to just go back to like slideshow mode or whatever.
Yeah, do it one more time.
I think so.
Then we're just gonna start and just pray.
Yep. If it gets knocked out, we'll just switch to single monitor. All right, thank you.
If it goes to sleep, it'll probably go black.
Okay. All right. Can everyone hear me? Perfect. So what we want to do is talk about Rapids. So briefly, we're going to talk about Rapids, the libraries, kind of our development process, what we were thinking when we were creating Rapids. Then Keith is going to jump in, talk about the data frame library some more. Are you going to show a notebook still?
Yeah, I can open up.
Okay, maybe we'll just do that afterwards, and then we'll just swap computers. And then afterwards, we have about 50 instances of GCP that we can pass out for people to play around with Rapids, kick the tires, hack some functionality with some of the dev team if you like, and go from there. So quick introduction, Josh Patterson, Director of Engineering at NVIDIA. I lead the Rapids project. And Keith Kraus, he's the engineering manager for our data frame library, CUDF. So data's growing. There's no hiding that. And because of this kind of growth of data, we see a lot of these big data systems. Hadoop, Spark, the whole ecosystem's really just blossomed since 2011. And one of the things that we realized very early on, both Keith and I, prior to this, were at Accenture Research Lab, and we were doing a lot of kind of big data systems, and we really just couldn't keep up with the amount of data, and so we kept scaling to larger and larger clusters. We were really excited when Apache Kudu first came out, and so we were doing a lot with Kudu as well, but we realized it's just like, we were just kind of still getting inundated with data, and we're trying to build this cybersecurity platform, and so that's really the basis of Rapids. It actually was us trying to solve a cybersecurity problem, and we just started playing around with Graphistry, a graph visualization library that's fully in GPU memory, and some of the GPU graph analytics libraries like BlazeGraph at the time. And so the stuff we were doing on the GPUs, we could do in seconds, and it was actually keeping up with the volume of data, but all of our big data systems were just, we were just throwing hundreds of nodes at it, and it was just getting slower and slower over time. And so we said, what if we could take the GPU acceleration that we were doing for graph analytics and then apply it more generally to, essentially ETL-like things, machine learning, et cetera. And so we kept playing around with GPUs, but we realized there were some barriers to adoption. There's a lot of data movement. So every time we want to do something with a GPU, we're moving data back from host memory to device memory and back and forth. That really killed productivity. And then there were too many makeshift data formats. Early days of GPU programming, every library wanted to do things in a slightly different way. There was no kind of concept of interoperability between libraries. And so even if I did want to keep something on the GPU libraries couldn't talk to each other. So I would still have to send it back to host, do some type of copy and convert, and then bring it back. Writing CUDA C++ is hard. Most of the data scientists that we were working with at Accenture Labs were Python, Scala, Java developers. And so writing CUDA kernels was not the most pleasant thing. And at the time, there was really no great Python APIs outside of deep learning. And so when we joined NVIDIA, one of our first things to do was connect a fully in GPU memory database, MapD, now OmniSci, to something like Graphistry. So what we wanted to do was show that we could hold essentially about a month's worth of cybersecurity data for this large firm and be able to do real-time queries of like, here's different patterns in net flow and different types of data, and then visualize these graphs. So here's people coming into the network, here's what device they were propagating to, et cetera. The query side was taking sub-second, the visualization side was taking sub-second, but moving data between MapD to Graphistry would take essentially about 90 seconds to 2 minutes, mainly because of the copying it back to host, converting, and then copying it back. And so if you have a machine that has 8 or now with the DGX2 16 GPUs, and 16 GPUs can do things really fast. But then if I'm trying to copy all that data back to host memory, I still only have 2 cores, 2 sockets of CPUs to work with. And so with the copying and converting was always our biggest bottleneck. So we realized we had to do something where we could essentially get rid of this. Just keep data on the GPU, pass it back and forth between applications, really leverage things like CUDA IPC and other protocols so we could just have one library, communicate with the next library, and hopefully just pass pointers to the data. We never really wanted to copy data at all. Also, GPU memory is scarce. Most GPUs are 16 gigabytes. Now with the V100s, they're 32. And so one of the things we wanted to do is also remove copying. So even copying was kind of a problem because we just didn't want to run out of memory on the GPU. And so at the same time, Apache Arrow was really kind of picking up steam. So this was around 2016. And so I really love this diagram. I think it very succinctly just says what the problem is. In the big data world, everyone was serializing and deserializing data between these different applications. And what they wanted to move to was basically Arrow, and everything could just read and write to Arrow. We wanted to do the exact same thing on the GPU. Every application on the GPU could just read and write Arrow, essentially. The beautiful thing about this was there's not that many GPU libraries that were doing data science. Basically saying, hey, this is a standard was very easy when you had something like Apache Arrow, and we're just like, okay, boom, done. This is what we're going to do on the GPU. And so that's really the foundations and the background of Rapids. So Rapids, it's basically Apache Arrow is how we represent data in memory. And then on top of that, we have different libraries. cuDF, our data frame library, cuML, our machine learning library, cuGraph, Graph Analytics library. And then we have integrations with things like PyTorch and Chainer, CuPy for deep learning. And then we have a host of different visualization integrations. We recently released a library called QXFilter, which was essentially a nod to the original cross-filter library. Essentially it does cross-filtering on the GPU, and then you connect it to things like Kepler GL or D3 or whatever visualization library you want. And so this top half of the slide actually came from a Spark slide. So essentially we're replicating a lot of what happened in the traditional big data community, but just on GPUs. So instead of reading and writing from HDFS, Spark keeps everything in memory. Similar to that, we want to keep everything in GPU memory. So instead of reading and writing back to system memory, let's just remove all of that, leave everything on the GPU. Let's have protocols for communication, standards, as well as a host of libraries to do everything from group bys, joins, string functionality, reading different formats, Parquet, JSON, XML, what have you, directly in Arrow on the GPU. And we really try to keep as much on the GPU for as long as possible. And with that, we're seeing pretty amazing performances gains. And one of the reasons why this is possible is really because of just kind of how NVIDIA works. We basically are working with the stack all the way up from the CUDA level and the hardware all the way up to the application. So Rapids is fully open source, and all of our algorithms are open source. But we also can go back to some of the CUDA engineering. We're like, hey, this functionality in CUDA doesn't really work for this application. Can you add this or can you add that? Even all the way down to the hardware acceleration. And so there's some really cool things that we can do with the tensor cores. We're experimenting with new things with the ray tracing cores that do different types of distance calculations for things like KNN. And so a lot of that's still very experimental, but it's really amazing that we can actually go over to the hardware guys and be like, hey, if you guys would add this in the next generation, it would really help this part of the data science workflows that we have. And so I think that ability to iterate is one of the reasons why we can move very quickly with Rapids. So before we jump into all the details, how to get it, currently you can download source code from GitHub, Conda install, we should have pip install in the next couple of weeks, and also containers, Docker Hub or NGC, NVIDIA GPU Cloud.
Take questions at the end.
Actually, we have time.
Sure.
Go for it.
Can you go back to this previous slide and one more? In this case, the error is going to be in memory.
Yes.
So if you want to store the data in a persistent manner, you still need some sort of database like Cassandra or something related to this.
Or you could just do like Parquet.
Yeah, we're gonna touch on accelerating I/O, like file loading into GPU memory, then a little bit later in the presentation.
Okay, but then if there is Parquet involved, then you still need to do HDFS write and read, and then do the error in memory.
Yes, but you don't have to like constantly do it over reading and writing from Parquet. You ideally would want to do that once. So read from Parquet, and then depending on how large your data is, obviously, and how many GPUs you have. But
okay, so if we are comparing with the other processing reading from this, we will still have an HDFS data source. We will read from there, and then that will be materialized into an arrow.
yes,
And then you do computation on top of the arrow.
correct.
And then you will output this into, again, like an arrow.
Correct. So first I'm going to start talking about some of the machine learning and graph analytics side. Ultimately, here's our full roadmap. NVIDIA spent a lot of their time starting in the deep learning space, and essentially we're just expanding out. So I think most people think of GPUs as almost synonymous now with deep learning. We want to do the same thing for machine learning. And so we spent a lot of time with GBDTs, gradient boosted decision trees, and XGBoost. And now we're just essentially expanding out to more things. So random forests, linear regressions, k-means, KNN. We had a graph library, NVGraph, that was single GPU. We're going to expand upon that as well. We're bringing in some other open source libraries like Gunrock, a lot of the work out of Georgia Tech, the Hornet, which is now Stinger. Actually, now it's
Now Hornet, it was Stinger.
It was Hornet, now it was Stinger, now it's Hornet. And so we're bringing that into the cuGraph framework as well. And I'm going to talk more about some of the performance improvements, but I don't know if you all can see the chart on the right-hand side of the screen. But essentially, about a 90x improvement on XGBoost on about a 100 gigabyte data set. And so we show kind of the scalability as you increase the data size and the time. And so that's pretty impressive. And just from some some field success stories, we've heard some customers say they've taken 100 node XGBoost clusters and basically moved it down to a single GGX2, and they're still getting about a 20 to 25x improvement. And so the density of GPUs is really exciting. And so I'm going to talk about that for a little bit. So our first real workflow was just looking at mortgage data. So we took all the mortgage data that's publicly available from Fannie. And so it's about 400 gigabytes of data. And so you have two data sets. You have acquisitions and performance. So raise your hand if you're familiar with buying a house. Okay, so like this middle section of people and that guy. Okay, so when you buy a house, there's like really two processes to it. First, you apply for a mortgage, and that's the acquisition side. And then you have your payment history, so you keep paying it over time. As a mortgage lender, you actually want people to pay for their mortgage for all the term, so 15, 30 years, what have you. You don't want people to prepay. You also don't want people to default. So prepaying and defaulting are both bad. So you want people to apply for a loan, get a loan, pay that loan over time. And so with this data set, you have two data sets. You have the acquisition side, which is borrower characteristics, your FICO score, your debt to income, your income itself, and then all these other various characteristics of the borrower, and then you have their payment history over time. And so what we wanted to do was essentially combine those two data sets and figure out, based on current characteristics of a loan, current state and temporal components, like how the median family income is doing at a certain time in a state, would this loan either prepay or default in the next year? So kind of a simple exercise. So we combine these two data sets, we join them, we do this kind of rolling window to figure out when a loan's actually, or what's happening to this loan in the next year to build a training set. And then we hold some of the data out of sample to do predictions. And so the ETL processing of that, so the joins, the group bys, all the different variable creation, you can see what is on a 20 node, 50 node, and 100 node Spark cluster. These are 8-core nodes, 64 gigabytes, so they're relatively weak nodes. But pricing-wise, like the cost of 16 GPUs on AWS is roughly equivalent to about 30 nodes. So if you wanted to put this somewhere on this chart where it's dollars for dollar the same, it would be somewhere right around here. And then here's processing time of 20 nodes, 50, and 100. And so doing the end-to-end processing with cuDF takes about 40 seconds on a DGX2. The ML prep is a little bit longer because we're copying all the data back from system memory, an arrow on the system side, and then back to the GPU. And then we're doing XGBoost training. And so this is kind of just between scaling up with more GPUs versus scaling out. So DGX2 has 16 V100s, 32 gigabyte GPUs, and they're fully connected with NVSwitch versus 5 DGX1s, so 8 GPUs per node, and then we have them connected by 4 InfiniBand 100 gig NICs. And so this is 40 GPUs and this is 16. And so this does perform faster, especially in ETL. But what we really found interesting, I'll just jump to it. What we found interesting is the XGBoost time between 40 GPUs versus 16 wasn't that drastically different, and it was really just going out to network, kind of hurts performance a little bit. And so that was a really interesting thing. Another interesting thing is if we had a smaller data set where we never had to write it back to system memory. So obviously with 400 gigabytes of data, we can't keep that all in GPU memory and do processing. So we had to write the intermediate results back to system memory. Here with a 35 gigabyte data set, we can actually keep it fully in GPU memory the whole time. And so you don't actually have this ML prep time. You don't have to move it back. And essentially going from arrow to a D matrix is pretty much an instant conversion. And so instead of having this time in red, it just essentially goes to 0, and you still get the speed ups of machine learning. And so one of our engineers on Rapids, he actually placed 8th in the plastic Kaggle competition. And so a lot of what he was doing was essentially just reading in data, processing it, and then running XGBoost and trying to bootstrap labels for an RNN ultimate training of this data set to predict essentially stars and how to classify stars. And so we're going to have a blog coming out about that in a few days. But it's a really cool example of when you can do things 50 to 100 times faster. He basically said, I have no knowledge of interstellar classification, and he didn't really even try to understand the actual properties of stars. It was just kind of more of a brute force. I'm just going to do a bunch of feature engineering, and then I'm going to run it through XGBoost, and then bootstrap that to feed into an RNN. And he basically placed 8th out of 1,000 people. It was a little bit outside the money, but pretty impressive results, just kind of showing what one single GPU can do with brute force.
When you're increasing instances and the XGBoost, also the data prep time, like basically return on investment is decreasing. How NVIDIA Rapids is able to increase the data prep amount of data transfer that the XGBoost significantly? Because it looks like the adding more nodes doesn't help on the Spark side.
That is correct. And so it's a very common thing. Once you get past like 20 nodes on Spark, you're really not going to get significant more improvement on XGBoost. And so you have to start scaling up because of communication. And so it's just one of those, it's actually a really tough business problem. What do you do when you have a larger data set that you want to run some type of gradient boosted decision tree on? And you know that scaling out doesn't really help you. So then you have to start buying these fatter and fatter nodes. And so that's actually one of the prime reasons why we built Rapids. And so you just have more density with GPUs. So if we know that scaling out is going to lose performance, if you can scale up a lot further with GPUs, it improves the total compute time. And here's just a few more. So these are single GPU benchmarks. So comparing just a single V100 to a 20-core CPU, TSVD, PCA, and dbScan. And so within Rapids, we've released those three algorithms, single GPU. We've integrated Facebook's KNN from Face, and we have k-means as well. In our next release in a couple of weeks, we're going to have common filtering, GLM. In 0.6, we're going to have random forest, ARIMA, and UMAP. So I don't know if people have been following in the PyData community, Leland McKinney's. He has this really cool dimensionality reduction library called UMAP, and it performs significantly better than most methods. And it has a really great visual clustering of data when you map it out. And luckily, it is a very parallelizable algorithm. And so it's essentially a KNN with a stochastic gradient descent on top of it, which are both things that we can do well on the GPU. So we're really excited about working with him to implement that. So we have a couple engineers working on that, and we should have that out in the March timeframe. And then finally, graph. And so we're just looking at pip installs for Network X, and one of the surprising things is how many people are using Network X, just graph analytics. And on the other side of the world, we spend a lot of time on the CUDA side thinking about graph. So we had NVGraph for probably 3 years now, but these two worlds just never talk to each other. And so the NVGraph was really just for HPC, people who are very used to CUDA programming. And Network X is a very straightforward Pythonic way of doing graph analytics. And so cuGraph is kind of one of our things. We just want to make it very simple and Network X, GraphX-like for people to do graph analytics, but get the speed of GPUs. And so, here's just some early benchmarks of our PageRank versus Network X's PageRank. And then we're just going through the algorithms: breadth first search, triangle counting, Jacquard similarity, and just systematically doing single and multi-GPU implementations for all these graph analytics. And then having Python interfaces where they can read and write to Arrow, as well as other formats, COO, CSR, etc. And then we're going to talk about cuDF for a bit. Really like this diagram. When we first launched Rapids, Jensen, our CEO, he was like, he wanted to feel what a day in the life of a data scientist was like, and it's kind of a hard thing to diagram out what a data scientist does. And so one of our designers, he was kind of just sketching out different things. We kind of had some doodles, and then he had some clocks, and he kind of kept playing around with it. He kind of, stumbled upon this, and we really liked it. And it's kind of true. And so we then asked G-Way, the guy who does a lot of our Kaggle competitions, how is it now versus with Rapids? And so let me be honest, Rapids has been around for 3 months. There's a lot of this is kind of where we ideally want Rapids to be. There is now a lot of, this is undocumented, this broke, then he has to go ask us, and we have to hot fix something for him. But hopefully in the near future, it'll be this seamless. People are just doing workflows, they're powering through things. And just as a comparison, we were on the Fast AI forums and we were talking about the same Kaggle competition. And a lot of people were spending 2 to 3 hours just doing group buys on the data and other simple manipulations, because the data set was about 20 to 30 gigabytes. And they're like, it would be really useful if we had some type of GPU accelerated way to do some of these feature engineering. We're like, well, we're glad you said that, because there is. And he did it, and here's how he did it. So that was really exciting to show people who actually had pain points today, someone who was doing it already on GPUs, and doing these same group buys essentially in tens of seconds. So with that, I'll pass it over to Keith. So excuse us for 1 second while we change the mic. Any questions right now?
I'm going to just ask you to kind of validate. In my opinion, why there's a different community. NumFOCUS is easy to use. It doesn't perform for large systems. The barrier to entry of previous large graph systems was very, very high. And so you just kind of deal with your computer running overnight on Network X. And so is this going to help kind of make an easier barrier to entry to graph-oriented
I'm just coming from a cybersecurity background. We've been using graph analytics for the last 5 years, and but if you're, with Spark GraphX, we were just really surprised at how long it took to run things that we can do pretty much in seconds on a GPU. And also, graphs are not too hard. People think things are like essentially like 50 gigabytes of data for a graph problem, which is kind of absurd in a way. Like, you're just basically replicating your data a ton, and then throwing as many CPU cores at it as possible. And like with the RTX 8000, it's a 50 gigabyte GPU. And so most companies, we were talking to one connected car, major Detroit manufacturer, all of their data for a whole year is 40 gigabytes. You could put that on a single GPU and then do PageRank or any of these algorithms in literally seconds. And so by making it more Pythonic, by following kind of known standards, and so giving people that Pandas and Network X put on GPU, I do think that graph analytics is going to kind of blossom quickly.
I would also add we're kind of one of the things that we're really focused on across the Rapids ecosystem is solving the data pipeline problem for you, so you don't have to build that really annoying and non-performant glue code in order to get data from one library to another library to another library. We standardize around Apache Arrow so that these libraries can hand off data to one another really, really efficiently. And when conversions need to happen, we handle that for you on the GPU, which makes it almost free, basically. All right, so with that, I'm going to talk about cuDF, which is our kind of GPU data frame library. So I'm Steve Kraus. I lead a lot of the Python development on cuDF and kind of some of these other Rapids libraries. And so cuDF, it's a GPU-accelerated data frame library that's based on the Apache Arrow data format, but is exposed to end users with a Pandas-like API. I would say it's like 95, 99% the same as Pandas. There's just some very small differences. Kind of the main one being that we don't support multi-indexes on rows. We will support them on columns in the future. But it exposes all of the things that you normally use Pandas for today for like your feature engineering. Stuff like unary and binary ops, joins, merges, group bys, filters, user-defined functions, which I'll touch on more later because there's some really cool things that we can do there with the Python ecosystem and GPUs. And then also some accelerated kind of I/O type things like loading CSVs, loading Parquet, loading ORC, et cetera, and how we can actually leverage GPUs to accelerate those things. And so cuDF today, it's it's in really two parts. There is a kind of CUDA implementation underneath with a C++ API, and then there is Python bindings on top of it that make it look and feel like Pandas, as well as integrate within kind of like the PyData ecosystem. And so kind of on the CUDA C++ side, you have a usable API, and then it also kind of exposes a lot of your lower level mechanisms, like importing and exporting data while keeping on the GPU using CUDA IPC, which is inter-process communication. It's basically a virtual handle that you can think of like a pointer to allow you to share data across different processes without having to actually kind of serialize the data and copy it off the GPU, for example. It has all of kind of the low-level CUDA kernels, as well as like thrust calls, for example, to perform all of your kind of like element-wise math functions and other kind of reduction functions, group bys, joins, etc. And then also things like sorting and kind of all the operations, they end up being low-level CUDA implementations in order to kind of squeeze out the most performance possible. And then kind of with the Python interface on top of it, like I said, we integrate with the PyData ecosystem, so things like NumPy arrays, PyArrow tables, Pandas data frames, basically anything with a memory view we can import. And then also we use the Numba library heavily. So for those of you who are not familiar, Numba is a just-in-time compilation library that basically allows you to write very naive Python functions, and then it will compile it down to machine code, and you can target that for either CPU or the GPU. And so what that allows us to do is basically say you're missing a function that you need within cuDF, or you have some kind of custom function that isn't really exposed in the normal Pandas or cuDF API. Instead of using like apply in Pandas land and having it execute in pure Python, you use apply in cuDF, and it actually JIT compiles that function to GPU code and then executes that on the GPU, and so you still get the GPU accelerated speed that you expect. And I will add Pandas. It's somewhat easy to get out of doing vectorized kind of operations in Pandas. we make it very difficult to do that in CUDF without hiding kind of the functionality. And so in general, if you can do it in CUDF, it will run on the GPU and it will run fast on the GPU. Okay. All right. And kind of along with CUDF, we recently yeah. So we recently released a string library for doing kind of string operations on the GPU, and specifically large arrays of strings. And so kind of the API is going to follow kind of this, the API and functionality is going to mirror kind of the pandas kind of string functionality. And so you can see here some like initial performance results, and these have probably improved quite a bit since we've done this work, but kind of things like converting a string to lowercase, finding a substring within a string, or slicing a string, we're seeing really, really nice speedups. And we're going to be working over the next couple months to integrate this nicely within CUDF to provide a more native kind of string data type than what kind of pandas provides today. And kind of we like to work with big data. A single GPU, CUDF is a single GPU library. My data likely isn't going to fit in a 16 gigabyte or even 32 gigabyte card in a lot of situations. And so we're kind of tying into the Python ecosystem more by using a library called Dask. And so Dask is a kind of distributed computation scheduler that allows you to scale your Python workloads from anything from just using all of the cores available in your laptop to running on like a 1,000-node supercomputing cluster. And what's great about Dask, especially from kind of Rapid's perspective and using it for GPUs, is that it's extremely modular. That like scheduling, compute, data communication, handling like out-of-core caching, etc., is all really modular. And so we can kind of replace things as needed with our own implementations and kind of augment things to make it more GPU friendly and more GPU performant. And so what this allows us to do is basically run a Dask worker per node and point each worker to a single GPU in order to kind of have your exact same code that would run a single GPU run on multiple GPUs within a node, and then also run on multiple GPUs across multiple nodes in the future. And we're doing some additional work to kind of improve the data communication performance in Dask and make it more GPU friendly to take advantage of techniques like GPU remote direct memory access, which then can use like high performance networks like InfiniBand and 100 gig Ethernet with like Rocky. And so kind of the way this works, it uses the CUDF primitives underneath, exposes kind of the same high level API that you're used to. And then instead of kind of today, the state of today is you can do single node multi-GPU, and instead of using kind of the typical Dask data transport of serializing data and then shipping it over a TCP socket, what we actually do is get those CUDA inter-process communication handles and ship those, and then the remote worker reads that handle and copies the data GPU to GPU peer-to-peer. And so then that'll take advantage of things like NVLink or PCI Express peer-to-peer copies, which gives you like an order of magnitude better performance than serializing and shipping over a TCP socket. And then kind of we're working towards it now and should be released hopefully in the next few months. We're working with a library called OpenUCX, which will then allow us to kind of do the same thing across multiple nodes. And so using networks like InfiniBand, 100 gig Ethernet with Rocky to do remote memory accesses across nodes without the data ever having to go back to host memory first. Yep.
So the goal is kind of going towards you kind of forget. So I have a data frame that's like 100 billion frames or something.
Yep.
And traditionally you have to filter it or it's downsample it or lots of those things. And we're going towards just being able to kind of deal with the data set.
Yep.
Right now it's within the multi-GPU.
Yep. And kind of towards the future as well, we will handle doing, even if you just have a single GPU, we will handle doing out-of-core and spilling to system memory and then moving it back to the GPU as necessary. But the whole idea is you just point to us your large data set, we figure out how to partition it, how to perform all of those operations across the different workers on it, and you don't worry about that at all as an end user.
And one more thing on that one. What we're seeing is a lot of some of the higher end network cache storage. Some of the network cache storage is actually faster than local storage and actually converging on speeds pieces of system memory. And so with GPU, remote direct memory access, and eventually with some other technologies where we can write directly from network cache storage to the GPU, we soon will be able to use network cache storage, basically the massive spillover buffer. And then if you have this 100 terabyte NAS, you can just stream it directly to the GPU. So obviously, with this, you probably have more than one GPU, but you might not have more than a single node. You might only have 16 GPUs or 24 GPUs. Still having access to 100, terabytes of data is really exciting.
And so then kind of on the machine learning side and the graph side, it's kind of, we're doing the same thing with Dask. But instead of using kind of OpenUCX and handling it in kind of the traditional analytics, very elastic way, it's your kind of more static way where, like in the ML world, if a worker dies, you just kind of have to restart running the algorithm. You don't really want to run algorithms out of core too much because it's just not performant. And so what Dask allows us to do is it allows these workers to easily make calls to basically a lower level communication library. And so then that allows us to use things like MPI or Nickel or kind of whatever other collective communication library to do really efficient communications and just allow the Dask workers to make high level calls to essentially kick things off, synchronize things, and finalize things. And so kind of looking towards the future over the next few months, with the GPU data frame, we're looking to just continue improving functionality and performance across both single GPU, single node multi-GPU, and multi-node multi-GPU. With strings, we're looking to integrate it, basically integrate it completely into cuDF, where we want you to be able to do string operations on a column of your data frame and not even have to think, oh God, I'm working with strings, this is going to be slow, how do I do this? We want it to just kind of feel natural for you to use strings on a GPU data frame. And then we're looking to expand our accelerated kind of data loading, accelerated I/O support. And so today we have a GPU accelerated CSV reader that we're constantly adding additional functionality and performance improvements to. It follows the Pandas CSV API. And if I go to the next slide, we're seeing a more than 10x speed improvement over Pandas. We're not quite at feature parity yet, but we're quickly working up to it. We have a Parquet reader, which is a work in progress, and it's going to follow the API of Pandas Read Parquet as well, so still easy to use, very consumable. And then we have an ORC reader that there should be a public pull request going out relatively soon as well. And then kind of after CSV reader, Parquet reader, ORC reader are kind of further along, we're looking at things like JSON, XML, HDF5, etc. Kind of all of your standard, typical file formats. That what we've seen actually is that if we rely on like Pandas or other libraries to do the I/O for us, that actually becomes the bottleneck in the workload more than doing the rest of the feature engineering because it happens on the GPU. And on the left here, this is a chart from the Apache Trail log. So, and basically what it shows is that if you have a performant file system, the CPU actually quickly becomes the bottleneck in getting your data into memory. And so for us, if we leverage the compute capability of GPUs, we can actually accelerate this quite a bit and get this data kind of ready for you to do feature engineering on much, much faster. And then also, so we've been working with Anaconda and other members of the community to kind of help drive this thing called the Python CUDA array interface. And so it's similar to the NumPy array interface, but it's basically a standard metadata on how to describe n-dimensional arrays on GPUs. And basically the idea behind this is to allow different GPU array libraries to talk to each other efficiently and not have to essentially copy back to host memory and NumPy to then just copy back to the exact same data format on the GPU. And so the first adopters are Numba, CuPy, and PyTorch. And so Numba kind of has bidirectional CUDA array interface, where basically you can go from a PyTorch CUDA tensor to a Numba device array, and there's actually 0 copy, 0 conversion. It's basically a free operation. Same thing, CuPy to Numba. CuPy actually supports it as very recent, I think a couple weeks ago, maybe. CuPy supports coming in as well, so you can pass between a Numba device array or a PyTorch CUDA tensor to a CuPy array. 0 copy, basically just access the pointer to the data, and you're good to go. PyTorch supports the array interface going out. It's work in progress and supporting it coming in. So you can't quite yet create a PyTorch CUDA tensor from, or sorry, you can't quite yet create a PyTorch CUDA tensor in a zero copy from like a number tensor, for example. And so join the movement. Kind of Apache Arrow, Rapids, the GPU Open Analytics Initiative. We're all open source, just trying to kind of leverage the power of GPUs and improve kind of the data science and GPU accelerated data science ecosystems, where any kind of bug reports, issues, feedback, feature requests, documentation, anything, it all really, really helps us. And especially, it really helps us to prioritize our development and understand where the gaps in the community are that we should try to address. And we want to give a huge shout out to the Google Cloud Platform. They provided us with instances to kind of give you all to allow you to kick the tires today. And kind of in just a few minutes, we're going to spin some of those up and then kind of work hands-on with you in either hacking some features together or even just kind of using CUDAF, QML, however you want to use it. And so huge, huge shout out to Google for doing that. And then the Rapids container is also available on Kubeflow today, I believe. And so with that, we'll take any questions before we kind of move into a more hands-on version. Yeah.
Does all the software work on Windows as well, or would you say just use my Linux machine?
So the question is, does the software work on Windows or only Linux? As of today, it's Linux only. We haven't decided on Windows support yet. There was some blockers on the CUDA side as to whether it was possible or not. I believe some of them have been resolved, but I'm not sure on the status of all of them. It's on our minds. If it's possible, we will support it in the future, but we can't make any promises. Yeah. Yes.
Sorry, it's like changing CPU for machine learning. You're basically taking CPU-based machine learning and different algorithms and everything, which you give for all the analytics and putting everything to the GPU to do that, right?
Basically, yeah. So the only other thing I would add to that is we are exposing like a C, C++ API as well for non-Python users. And this also allows us to expose it to other languages in the future, things like R, or kind of any other language that can consume a C, C++ API that people would know. But on the Python side, yes, we are mirroring the Pandas API, scikit-learn API, NetworkX API, to make it just really easy to use and consumable for kind of traditional developers and data scientists. Yes?
Are those GCP instances available on the marketplace already for us to spin up?
Not quite yet. We are actually going to just provide you an IP address that you can SSH into to play for today. As far as I know, we do not have any kind of, AMI or anything on the marketplace today.
Is that on the roadmap?
Possibly in the future. Today, the best bet is just to spin up the container, which it gives you a completely set up environment ready to go, and then also has some kind of demo notebooks built in that you can play with.
And with that, I mean, that's also why we're common to, so most people, instead of AMIs or GCP results, they rather just focus on what they want themselves upon themselves. So, yeah, I mean, honestly, does anyone use AMI as opposed to just different themselves? I mean, yeah. I mean, we can do it. I mean, we just haven't really heard the demand for it. Most people are like, the main demand we've heard is people really want it.
An AMI would probably end up just looking like install miniconda, create an environment, conda install, CUDF, conda install, QML.
I'm thinking for students.
Okay. Yeah. Okay. Yeah. Yeah, that will make sense. Yes.
Which pandas operations do you see the greatest speed of using like this PDF?
So kind of almost anything where you're essentially accessing a large majority of the data. So joins, group bys, element-wise operations, unary operations, kind of any operation where you're having to scan the data and you're not essentially just doing a random access on like a single element, you'll see pretty massive speedups.
Will they allocate the GPU memory?
If you're using QDF, yes. When kind of as we continue to improve support for Dask QDF, if you use that, no. Yes.
Dask flow, we have kind of Dask queue there for a single machine, and then Dask will distribute a lot of computation across multiple machines, kind of like MapReduce. It's also Dask responsible to output, like kind of reduce fetch output that every single data that is being computed by a single individual CDF computation of the kind of this
So it depends. It depends on the operation. So for things like element-wise operations or things that are like embarrassingly parallel, it's just like a simple each worker does its own thing with QDF underneath the hood. For things like joins, group bys, where it's more like you need to actually communicate between the workers, then there is specific algorithms built into Dask QDF to handle that. But I guess I'm not following the question.
So I'm trying to understand if Dask is actually allowing the workers to communicate under the hood, or if the QDF actually has a built-in inter-process communication to actually.
So the way the communication works today, I'll explain it both today and how it's going to be in the future. So today, in the QDF library, there are custom serialized and deserialized functions that register with Dask. And so Dask allows you to register essentially custom functions as to how do I serialize this object into something I can ship over wire, and how do I deserialize. Okay. Today, basically, our serialized function just gets an CUDA IPC handle, so this inter-process communication handle that can be shipped over a wire. The deserialized call basically reads that handle and then copies the data to its local GPU. And so as far as Dask is concerned, basically whenever it needs to communicate data between workers, it's essentially just shipping, like you can imagine, a single int64 object, basically. And then the rest of the actual data movement happens at a low level in essentially the NVIDIA driver, basically handling a peer-to-peer GPU copy. In the future, we're looking at using a system called OpenUCX, and then in like machine learning and graph analytics, we'll be looking at using like a collective communication framework like NICL or MPI. And so in that case, Dask is basically just making calls into essentially what would be like a wrapper on top of like a C++ function, which then handles all of that communication kind of below Dask, basically.
And in this flow, what is the failure is handled? So let's say one node fails. Does Dask actually schedule another worker, or actually?
Yeah, so it's different between, so like for QDF, for example, it will handle a node failure and then reschedule the work onto a different worker. And basically, if it needs to say like restart earlier stages based on like the task graph, it will do that onto a different worker. For QML and QGraph, because you can't really handle that elasticity in a like performant way. Basically, you can think of the jobs as more like barriers, where if any worker fails during the job, it needs to essentially restart that job. And so at that point, it'll just act as a barrier. If any of them fail, it'll kick off all of them again across the workers. And then the Dask workers, you can run them with what's called the nanny process, which will basically detect, hey, this worker failed. I need to actually restart this worker so it's ready for more work properly.
How far along would you say the QStrings library is in terms of like goals for future development?
It's very early. Like we just released it like a month and a half ago.
Yeah. Maybe. Yeah.
Yeah. So
I just heard about it like a few weeks ago, and it kind of blew my mind. I was like, strings in the GPU, it's crazy.
Yep.
But for now, like the operations I saw you showed there were like really basic.
Yep.
But are there plans for? This might be a dumb question, but like, are there plans for regex engines or anything like that?
Do you want to answer that?
My very naive understanding of GPUs is that it's data parallel, and that doesn't make a lot of sense, but maybe it does.
The short answer is yes. The
Okay.
long answer is yes, but we're going to have to, this goes back into graphs, which is why I love graphs. The much longer answer is if you think of strings as a collection of graphs, words or nodes, their relationship to each other, or connections, or edges, and how apart they are from things. You can represent a paragraph as essentially the graph network, and then you can do things like Dijkstra, vector search, etc., to do more complicated regex type things very quickly.
Okay.
And so we do have a way to do this. That's more than theoretical. It's been like implemented in a very packaged way, and now we're trying to productionalize it. So regex is coming. I make no promises on when, but it's actually a really hard problem to use in parallel. But anything pre-regex, so like find, if I want to do, I want to know, every string that has keys in it, and then I want to know the location of key. I want to know words on each side of key. I want to do some type of bag of words, tokenization. Those things are doable today.
Okay.
Regex, just
like I said, what little I know, like that seems really hard. But
I mean, it's doable. It's something that we need to do. We will do. You can, for most machine learning, like NLP applications, you can get a lot of mileage out of bag words and other, just kind of tokenization and other things that are a little bit simpler. We were actually surprised that there was no string functionality when we used when we first started 2 years ago. And then we realized how hard it was. And there was kind of like string the whole, if you will. No, we can totally do it. And so it's actually one of the most exciting things about being in the video. Things that kind of the general public are like, no, that's too complex. You can't do that. There are people in the video who are like, oh yeah, I wrote a research paper on it in 2015. I didn't know anyone really cared about it. They're like, yeah, this whole community about data science. So we're exposing it.
Any other questions? Oh, yes.
So, that's it. But are there any companies already using it for
Oh, that's me. Actually, or either using it or taking the entire thing. The one that we talk about most is at launch, Walmart. We've been working with them for a very long time. They're using parse graph introduction today. And so, generally, the bigger the company, they're always looking for ways to reduce their competition. And so this is why we know that there are some kind of like less companies that are using it now, replacing like their something that actually uses clusters with just a single DGI for extra use. And one of the things that we're looking at a lot is streaming. And so there's a lot of people who will just constantly get 2 gigabytes of data every second, which is very ideal for GPUs. You just stream it in, calculate something, or lots of something, and then just keep doing that over and over and over again. Instead of doing a scale out, streaming like Blender, structuring, or something like what have you, you could have a much smaller GPU cluster doing the same thing. And the T4s is kind of ideal for that. They're still a lot harder. And so, so companies using it today. We've been working on this for over 2 years now, so this really is kind of us open sourcing it, making it a lot more easy to use, and ramping the team up, both internally and externally. So we have a lot of contributors outside of the team as well. People are using it. The goal, though, is to make it more feature complete. There's still a lot of issues. I mean, right now we have 146 issues on PDF alone. So, I mean, we're firefighting it and just keeping development, but the excitement is awesome.
I had another question about graphs too. What sort of in-memory format do you all use for graphs?
Today, CSR and COO. In the future, Hornet, which we're not going to call Hornet just because we're already tweaking Hornet slightly. But something that's going to be very similar to Hornet. I think at the last graph retreat that we had a couple weeks ago, I think we're going to call it Cubs. The coup graph structure. So Cubs will be the format of coup graph. But it's essentially a dynamic CSR. So think about all the great things about CSR compression plus the ability to do upserts.
Oh, well, okay.
I'm just getting stuff ready to go for the Google Cloud instances if people have other questions.
How many engineers do you have working on this?
Around, I think 50. So, it's been a lot in 2 years. Yeah. There's been a ramp up of the engineers on it. I mean, we started off with not 50, but it's growing really fast. So I'm excited. Also, we're hiring, by the way.
Yes.
Just in case any of you are, C++ Python developers and you love Python and making Python go really, really fast in parallel.
Alright, so at this point, I think feel free to keep answering questions, but myself and then a couple of the Rapids developers, so we have Paul over there, and then Dante. We're going to walk around, hand out IP addresses for GCP instances that you can kind of just SSH into and start kicking the tires. And the login information will be up here, but feel free to keep asking questions while this is going on. Absolutely. So do you want to just start at the...
So when I send you a list, I can...
Yeah. Should we just start at the... I'll start at the top, you start at the bottom?
Also, we need more...
Yeah, possibly. At this point, it's just going to be completely hands-on. Yeah. Do you want to start spinning up where we'll go around then? Who wants the GCP? I'm just going to kind of go around. Okay. Give you an idea. Well, it's not, it's only for a couple hours to play with. Alright, 35.225.206.95. And then the username and password are on the screen. Ready? Alright. 35.238.191. Huh? Yeah, he's spinning up more instances. I think we need more.
You might need more.
Okay. Nope. You are actually 104.184.200.21. And sorry, so in there is a Conda environment called Rapids. So just do source activate Rapids, and then you can install whatever you want. It has cuDF and cuML installed already. We forgot to install IPython and Jupyter, unfortunately, but feel free to install them. What? Yeah, you can put the instructions. SSH. We enabled password on. Got it. So. Which one did I actually give you?
35.1.
Oh, great. 35.224.206.45. Either PuTTY or Bash subsystem. Okay. Alright, so can I just give you the address to write down? So it's going to be 35.202.9.238. Yep, 231. And 35.226.124.169.
That's what it is.
Ready? 35.232.144.238. Yep. 35.232.190.166. Ready?
Right now it's over.
Alright, 104.155.165.5. 104.197.45.97. 104.155.164.176. 104.197.215.6. 35.224.114.19. Ready? 104.197.104.206. 104.154.47.111.
Easy to Yeah, just like that's what I was thinking. Everyone's 35 like that.
35.224.56.160. 35.232.130.235. Someone's at the bottom.